All right, folks, welcome to my first screencast for BMED 2210 this semester. I just wanted to recap what we talked about today in class. I had hoped to cover more than we did, but we had lots of fun, so didn't want to stop that. So I don't want to cram stuff in at the last second of a class and have it go right through one ear and out the other. So I thought we'd capture a couple more points I'd hoped to make today using the screencast. So first, one thing I wanted to emphasize is what we are learning is what some people call functional reasoning, which I mentioned in class. That means we take a system that we're interested in learning about or designing and breaking it down into functions. And from the chemical engineering perspective, that's often called processes or subunit processes. And they create what are called, the diagrams they create are called process flow sheets. And we're going to be using a lot of that. It's an extremely powerful way of thinking and very appropriate for a lot of things that biomedical engineers do, particularly when it comes to modeling physiological processes and cellular processes. So using this methodology, we will indicate processes as boxes. And there are a handful of very generic processes, which I've mentioned some today in class. One is mixers. Okay, we have mixers, we have separators, we have reactors, and we have splitters. There are some others, but these are the big four. And so just to indicate and illustrate what I mean by this very quickly, if you had a process where some kind of substance A is coming in one stream, and then a substance B is coming in another stream, then assuming this thing's at steady state, A and B is going to be coming out. That is a mixing process. Splitter is different. A splitter would be, and actually, unlike all the other units, we actually indicate a splitter with a circle usually. Splitter would be, let's say this A and B thing comes in, and let's say it's 10 grams per hour. Well, splitter might break it up into multiple flows of material coming out. It doesn't change the composition at all. It's just breaking up into multiple streams. So think of capillaries or arteries breaking up into smaller arterioles. Or imagine sharing a Coke with your friend. The composition of the substance that you're drinking is the same as what your friend is drinking, but each of you has a smaller amount. So for example, we might have, in this case, we would have A and B in each stream. But one stream might be, let's say, 1 gram per hour. Another one would be 2 grams per hour. And since mass is conserved and we're assuming it's at steady state, this would have to be at 7 grams per hour. So that's a splitter. A separator, and we talked a little bit about the different kinds of ways you can separate things in class today, but a simple one is a filter, for example. Suppose you had two substances, A and B, coming in. Then a separator might generate a stream that has pure A in one and pure B in another. Now, this is the most extreme case. You might actually have A and B in both. But let's suppose that in the incoming stream, the mass fraction of A in stream 1 is 0.8, and the symbol for mass fraction is a little omega. And that would mean 20% or 0.2 is the mass fraction of B coming in. So a separator is essentially purifying it. So you might have like a 0.9 coming out in A, and let's say 0.1, whereas down here you might have 0.6 and 0.4. Okay, so that would also be a separator, just not a perfect. It would not be effecting a perfect separation. But keep in mind that none of these processes in real life are, by any stretch of the imagination, perfect or ideal. Okay, and then the final sort of generic process that I want to introduce you to right now is the reactor. And let's suppose you had a chemical reaction where A and B react to form some other substance called C. So you might have a process something like this. You might have A and B coming in, and then C coming out. And that would be a reactor. And again, most reactors are not ideal or complete. You're probably going to have some leftover A and B in here as well, depending on the problem and what's actually happening. Okay, so basically we'll soon be doing mass balances, and you'll we're dealing with systems that are composed of one or more different kinds of processes, which could include a mixer, a splitter, a separator, and a reactor. Those are the major four that we're going to learn about right now. The other thing that we talked about in class today was estimation. And as I mentioned, the ability to estimate is a skill and it needs to be developed, and it is absolutely critical for engineers to be really good at this kind of thing, even in the days of Google. And an estimate is composed of a magnitude. It has units with it. Don't give me a number without units, please. And there should be some estimate of error. And in general, when you're just doing sort of what I would call a guesstimation or back of the envelope estimation, just deal with one significant figure. So, for example, when we did the golf ball estimation today, the answer was about 10 to the ninth. So 1 times 10 to the ninth would be the right way to present that information as opposed to, let's say, 1.63 times 10 to the ninth. We are just estimating, and it's just not a good representation of the actual error in that estimate if we're using more than one sig fig. There are various strategies that you can use to become a good estimator. One is to start with something that you really know, that you have a good feel for, because that will reduce the initial error that you have in your estimate. So today when we were talking about the washing machine process, most of you sort of reflected back on your individual clothes washing process as opposed to an industrial-sized one. And then start with that and reflect to something else that you don't know. You don't normally think of clothes in terms of mass, but you do think of bowling balls in terms of mass. So you could think in your mind, well, the amount of clothes that I put in the washing machine is probably weighs roughly similar to a bowling ball. So you could say around 20 pounds is a typical load of laundry, which might be a good estimate. Now, let's suppose you had no clue as far as the 20 pounds for an estimate, but you know that you have at least a pound. This is now we're on step 2, which is establishing upper and lower bounds. So another strategy or complementary strategy is to do upper and lower bounds to take a geometric mean. So let's suppose that you thought, well, I know that my laundry is at least 1 pound. I know that 1 pound is the absolute smallest amount that it could possibly be, but it's certainly not 100 pounds. So those could be your upper and lower bounds. And you could take the geometric mean, which I've indicated the formula for here. You would take the square root of your lower bound times your upper bound. So in this case, it would be the square root of 1 times 100. So that's the same thing as the square root of 100, which is 10 pounds. And remember, the goal of estimation is to get hopefully within factor 3 or 4. So a geometric mean will help you get started. If you really don't have a concrete enough idea to give an initial estimate with a single number, you can usually start with upper and lower bounds and take the geometric mean to get going. Another basic strategy is number 3. How do you solve a problem? The simple response to that is you give the answer. Well, if you can't directly give the answer to the problem, then it's slightly more complicated. What you want to do then is break the problem up into smaller problems for which you can give an answer for. And that's really what estimation is all about. You break in a big problem that's hard to estimate things for, and you break it up into smaller ones until you can eventually either start with something that you know or bound it and take a geometric mean and start from there. And then the final strategy is scaling. What you know is something that's on a different scale than what you're trying to estimate, but it's sort of related, you can initially estimate at the scale you're comfortable with, and then you can get another estimate, like the process that you're estimating for, how much bigger or smaller is it than the one I just made the initial estimate for. So for the clothes washing process, we thought about 10 to 20 pounds would be a typical load of laundry, but we were trying to deal with a 100-pound industrial level process. So in that case, we would want to scale up our initial estimate by between 5 and 10-fold. Now, just a reminder, to do the golf ball thing, I can demonstrate it here since I ran out of time in class. The golf ball's around the Earth. How many? Well, for me, I already knew that the circumference of the Earth is about 26,000 miles. Now, one team in class was very clever and somehow knew that jets flying 500 miles per hour would take, I think they said, 50 hours to go around the world, and they were able to estimate 25,000 miles. So it's really a good way to do that. There are multiple ways you could do that. One is time zones. There's 24 time zones, and you might happen to know that typical time zone is 1,000 miles, because you know that the United States is 3,000 miles in width, and there's about 3 time zones for the continental United States. So that's another way to get around this, to estimate the circumference of the Earth. Now, I want to get into inches because that's what my golf ball estimate's going to be. So I know there's around 5,000 feet per mile. It's actually 5,280. And I know there's about 10 inches per foot. As you know, it's actually 12, but notice I'm keeping everything to 1 sig fig. So really this should be 30,000, keeping that spirit of things. And so we have 3 times 10 to the 4th miles times 5 times 10 to the 3rd times 10. So we have 15, end up with 150 times 10 to the 7th inches. Notice these are crossing out, dimensional analysis, essentially. When you're doing these unit conversions, you want to write it out like that and then cross out the units that cancel. And so we have basically 2, we're rounded up, times 10 to the 9th inches is the circumference of the Earth. And we know that a golf ball is somewhere between 1 to 2 inches in diameter. So therefore, a good estimate, as I mentioned before, is about 10 to the 9th golf balls. All right, so that is an example of making an estimate. And that's all I got for the recap. Hopefully I'll have time to do short integrity videos on a couple of the fundamentals I want to make sure you're comfortable with, which is unit conversions, temperature, and pressure. And hopefully I'll get that done in the next day or two. Take care.